Okay, so it's a very exciting time to be in autonomous systems and flight software. At this workshop itself, I was very excited to hear Eddie's talk yesterday about work on the Mars 2020 onboard scheduling system. And just immediately following this talk, there's going to be further talks on autonomy and flight software relating to the Europa mission and then future rover autonomy, and then another talk on Europa lander. So to me, this is a really exciting time to be at this particular juncture and thinking about where we would like to be going in autonomous systems. So I'm going to be talking about a particular brand of autonomy, and specifically trying to get more spatially aware. And that's because in a lot of these space missions, it's very important to understand geometrically where the spacecraft is and how that relates to the different observations you're trying to take. And this comes out of a lot of work in my group, both in observation planning and most recently in support of the Rosetta mission. And so we're trying to take some of the functions that are traditionally on the ground in terms of analyzing the geometry, taking observations in particular geometric configurations, and move that on board. And we want to do that for a number of reasons, primarily to reduce the response time, capture transients events, be more effective at conducting the kind of science we want to do. So we're going to hear about different kinds of onboard data analysis. We're going to hear about mission replanning on board and what are some of the things that we can do with this capability. So the general flow that you're going to hear again and again today is that you take particular science data, you take particular images, you analyze that on board, and then that comes back through your command and control system in terms of replanning and changing the execution of what your spacecraft is going to do. And I'll give you quite a few science scenarios for that. And one of the key things here is that you have to know the relative geometry of where your spacecraft is, your target, your illumination, as well as have a good slewing model of your spacecraft in order to correctly plan those kinds of things. The kind of software architecture that we've flown in the past, this is, for example, the kind of software architecture that's been flying on the Earth Observing 1 mission for over a dozen years now, is a traditional layered architecture. At the top, we have what we would call a mission planning system. This is a system that's looking strategically at the states and resources of the spacecraft, looking ahead at the future observations, the future campaigns that you're planning. There's something like an execution system that you have. And in different of these prototypes, you'll see different versions in there. But fundamentally, you can think of this as a very capable sequence engine, as you might see on a state-of-the-art mission right now, plus different kinds of layered autonomy above that in terms of robust task execution, retries, where you have a procedural system that's able to understand enough about the lower-level tasks to keep the high-level planning system out of the mud, so to speak. And then we're going to have all of the traditional flight software for subsystems, the traditional hardware, and all of those things. And we're really also leveraging the fact that we will be processing the science data on board the spacecraft. And so just to kind of give you an idea as to where we're going and where we've been in terms of onboard science data processing, for roughly over the last decade, we've been processing thermal data on board the Earth Observing 1 mission, processing it and analyzing it in terms of extracting the strength of volcanic emissions, of thermal emissions for volcanoes, from forest fires, and analyzing it on board to determine what you're looking at, what's the temperature of what you're looking at, what is the surface area of what you're looking at, and then actually being able to change the future mission operations on board. And so if you're interested in this is actually described in gory detail in Ashley Davies' article on Remote Sensing the Environment. We've also been doing flood detection on board, so surface water extent to track flooding, and cryosphere detection, which is distinguishing between snow, water, ice, and land, different phases of water. All of these have used traditional sort of manually derived decision tree techniques, or in these cases, these SVM is support vector machine learning techniques. So these are classifiers that are learned on the ground, then are uploaded to enable the spacecraft to do these kinds of detections on board and then change its future operations. Some of the more sophisticated things that we've done on board are actually hyperspectral data analysis or imaging spectroscopy. Rob Green would be yelling at me if he heard me keep repeating the phrase hyperspectral. And what this is we have an instrument on board EO1, the Hyperion instrument, that can measure a large number of different spectral wavelengths of the data coming back, okay? So it actually measures between 0.5 and 2.5 microns at a 10 nanometer spacing. And that means it has over 200 spectral bands. So we see light in red, green, and blue, roughly speaking. It's seeing light in 240 different spectral bands, and that's very powerful. Every different chemical that you look at, because of its molecular structure, has a different spectral signature. And so this is actually showing on board, we're extracting the spectral signature of the different elements that we're looking at, and we can actually reconstruct this. Sorry, this is too small, so it's hard to see. This is actually our onboard classification, and this is a intensive ground-based semi-manual classification, which is the ground truth for this particular scene. This is showing mineralogy around Cuprite, Nevada. And so we're determining different, very subtle differences between these substances, kaolinite, alunite, and so on. These are very complex mineral signatures, and we can tell the difference between these on board. More recently, there's a great paper by Frankenberg et al., and then this is work by David Thompson, where they're able to do this even for gases in real time. So they did real-time methane detections at the Four Corners, basically in the Arizona, New Mexico area. This is with airborne data, but they can process this in real time, doing the same kind of spectral unmixing that we're talking about here. So this is really a fantastic, powerful technique that we're going to see more and more of in the future. Another example of what we can do on board now, this is from the texture cam system. And this is using a particular machine learning technique called random decision forests, or RDFs. And what this does is it's looking at an image field, let's say 40 pixels by 40 pixels, and it has a very simple set of operators that allow it to compare different spectral bands of different pixels in different regions. And texture cam actually also allows you to look at texture features as well. So you can extract mineralogical or geological signatures based on the texture of the image that you're looking at. And in this particular application, we used it to analyze images for clouds. This is from the IPEX CubeSat, and you can see that it's actually distinguishing between the limb, the clouds, land, and so on here. And this is actually stuff hot off the presses from the Earth Observing 1 spacecraft, where we're classifying these dark areas are high-intensity clouds, dense clouds, using exactly the same technique, random decision forests. So this kind of machine learning technique shows great promise in discriminating between these different kinds of things and allowing us to use that in decision-making on board. Another very interesting technique that we've been flying more recently is called visual salience. And this is a well-understood technique from machine learning, from machine vision, that looks for areas that are unlike the surrounding areas in a small visual field. And this is data from the IPEX CubeSat mission again, and this is showing that it's actually pulling out these 3 lakes. These are the 5 highest salient features in this overall image, and 3 of them happen to be lakes because the lakes are very different from the rest of the surface area around them. Note that it pulls out the lakes, but it doesn't pull out the ocean because the ocean is too large of an area. So the entire context is all water as well. This is also, again, I've interspersed, since we've started flying some of the stuff just in this last fall on Earth Observing 1. This is showing the same visual salience technique on a desert scene. And unfortunately, the blue is kind of hard to see here. But these streaks that are pulled out are the mountains and this dry riverbed by the visual salience technique. And the visual salience technique is very interesting because it's an unsupervised technique. It's not relying on some expert to hand label some images like the clouds and the limb and stuff like that, and then later get trained. It's just pulling out things that are exotic and unusual within the visual field there. So a lot of these techniques, we're trying more and more to push these on board. Another one is called the mixture tune match filter. This is, again, a spectral, something that's leveraging spectral information in the scenes. I showed you before where we unmix the data and then we compare it to a catalog to find out what substances we're looking at. The mixture tune match filter is slightly different. You have a catalog of things that you know you're specifically looking for, and it uses this maximum likelihood linear estimator to tell you whether or not you're looking at those scenes. We actually want to fly this on board because this technique is very computationally efficient. This is the number of pixels is n, b is the number of bands, and L is the number of elements in your library. So actually to do what's called your background rejection, so you want to reject what you see in all of your scenes, is actually only order n squared. That's actually quite challenging to do these things on board in near real time, as we'll see. And then the match is actually only linear in the library size, the number of pixels, and then the number of spectral bands you're looking at. So this is something that one of the prototypes I'm going to be talking about later, we actually demonstrated fits within the computational footprint to be doing in near real time on board. So all of these techniques give us better ways to look at the data on board. Another one that is actually a baseline for use on the NEA Scout CubeSat is Coedition. What's Coedition? If you have a very noisy instrument, like we're expected to have on the NEA Scout mission, which is a CubeSat, you can drive down your signal to noise by taking a large number of images and knowing that the noise is statistically likely to be very randomly distributed around that image. This doesn't work if you have like a bad pixel in your sensor. However, what you do is you co-add these images by aligning them, and you can drive down your signal to noise. Basically, you get a square root of n improvement with n images. And this is showing this technique done with particular different data sets. So we want to do that because we have to be able to do more and more with the instruments that are, of a certain limited quality. So now I'm going to switch gears a little bit and talk about some very specific methods that we've used for deep space scenarios. And specifically, we're looking at what we call narrow field of view targets in a small body. So we have sets of missions that want to go to comets, that want to go to asteroids, and there are certain wide area searches that you're going to do, let's say with a wide angle camera, and then you want to focus in on very specific things you find. Some of these things that you're very interested in finding are plumes. So this is actually Hartley imagery, and you can see these are plumes coming off this irregularly shaped body. This is Enceladus data, and you can see the plumes coming off of here. There's a lot of interest in doing this kind of reasoning and processing for Europa as well. In even other small bodies, even things like Vesta and Ceres, seasonally they believe they might have plumes. So why do you want to detect these plumes? You want to detect these plumes so you can respond and image them in greater detail. Okay? These are things that we have not been able to do thus far. Thus far, when we capture the plumes, we capture them by pure luck, by taking lots and lots of images. We want to do focused campaigns where we have a wide synoptic instrument that's staring always at the target, and then when we see these interesting events, we actually slew the spacecraft and image very specific targets. This is actually showing our latest and greatest. This is a collaboration with the Max Planck Institute. This is Rosetta data, and so this is the ultimate in terms of a very irregularly shaped body. The nucleus of the Churyumov-Gerasimenko comet is the famous rubber duck, so there's this two-lobed body, and this is actually showing our ground processing software that tracks plumes from one frame to another. So they take these image sequences of about 20 frames, and we want to track these from one frame to another because the scientists are interested in tracking the evolution of these plumes over time as they're under different illumination conditions, different injections of heat and photons into the chemical process that causes the outgassing that's the plumes. Unfortunately, what do they do now? They take one of these sequences, which by the way has 600 to 800 plumes in it, and a poor graduate student manually labels every single one of these plumes. So that's bad for two reasons. First of all, we all feel sorry for the poor graduate student. Second of all, that's not a unbiased labeling. That graduate student who's doing the labeling is most likely the same person who's publishing the papers on the theories of why these plumes form and under what conditions they form, or at a minimum, he or she is probably in the same research lab as the person who's writing those articles. So you want an unbiased catalog of these plumes for everybody to use in testing their theories. From an autonomy standpoint, why do we want this? Well, we'll see later on. We're very focused on scenarios where we would detect these plumes and then image them with much more focused observations. The particular techniques that we use by plotting this into sort of a 1D space and looking for peaks in intensity is actually not very well suited for onboard use because it's actually computationally intensive. But there are other techniques. In fact, let's see if I go back. These techniques, we actually fit a convex hull to the object and look for brightnesses that are extrusions to that are well designed for onboard use. In fact, I think this Thompson and Wagstaff 2013 article has an analysis of the computational complexity of that approach. It's order n squared in the number of pixels, so it's not bad. Okay, so now you've heard a lot about what kinds of instrument processing we want to be doing on board these spacecraft in flight software. What do we do once we actually know these different things that we want to observe? We now want to change our plan. Well, in an Earth observing context, it's very challenging. You have a spacecraft. This is actually looking at something like a WorldView 3 or WorldView 4 class spacecraft, if you're familiar with that. These are commercial imaging satellites that are very agile. And as you're flying overhead at low Earth orbit, let's say 700 kilometers, you have about, from horizon to horizon, about 10 minutes if you're looking directly underneath your ground track. The first thing you do is you have to throw out half of that 10 minutes because all of these imaging people want to keep the relative viewing geometry similar. So what that means is you're really restricted to looking in front of your spacecraft for comparing among these image signals. So now you have 4 minutes, and so you might be looking out here at some targets nearer to the horizon, let's say 20 to 35 degrees, and then when you see interesting things, you might actually image them, let's say at nadir, to maybe 8 degrees in advance. This is very challenging here. You've now said from here, 5 minutes out, to here, let's say 2 to 3 minutes out. In those 2 to 3 minutes, you have to analyze the imagery, you need to compute your response, and you need to execute it with your slew model. So in other words, if you're looking at a highly agile spacecraft, you're probably looking at a few degrees per second slewing rate in terms of both your acceleration degrees per second squared and in terms of your max slew rate. So that's the profile that we want to fit in. So we actually have two sets of planners that we apply simultaneously. The first is the Casper onboard planner. And Casper is very good about reasoning about states and resources and timing. And so I won't go into too much detail about this, but basically it's modeling the spacecraft as a set of different timelines, and the different observations, the different activities are then fighting over particular resources on those timelines. You can think of the timeline as a semaphore existing over time to make sure that you don't plan things with resource conflicts. The second thing that we need to think about is pointing as a resource. And this is actually extremely challenging because the geometries are constantly changing. In this low Earth observing case, this is a very horrible, complicated diagram that I'll now try and explain. Hopefully I'll succeed. This is sweeping forward in time. Let's imagine at time 0, the spacecraft is pointing at nadir, and there is a target at the horizon, let's say 42 degrees out there, that you want to look at. What does that mean? As you're flying forward, you want to slew forward to meet that target, but your spacecraft flight path is actually also bringing that target towards you, right? So the time at which you can observe that, this blue line shows a single fixed point as it's moving towards you. And by the way, that's not linear, right? Because you can think about the way the curvature of the Earth and the horizon and everything works. It's actually not even the trig function. If it was a flat Earth, it would be the trig function, right? So this line here represents a fixed point at the horizon as it comes closer and closer to you, let's say roughly 2 minutes out, okay? You need to find the intersection of these two lines. This is where the target is moving towards you, and this is your slew rate. And as I said before, almost all, to a first approximation, your slew model is constant acceleration to a peak rate. So really, this is like a second-order polynomial, right? So you're solving for this intersection when you're slewing forward to a target that's meeting you. This here shows the opposite. Let's imagine you're looking out and you realize you want to look at something that's closer to nadir, okay? You're going to slew back to try and reach that target. That's this line here. This line is going down, not up, so it indicates that you're slewing back towards nadir. As this line shows that the target is running away from you, right? As you're slewing back, it's moving further and further, closer to nadir and behind you. So basically, these are route finding problems that you need to solve on the fly, and that's exactly what the software does. You also have to solve this identical problem in the across-track version, right? And in the across-track version, the dilation is not nearly as bad, but there is still dilation. Why is that? Because as you're looking out, everything's sort of a smaller angular field of view, right? So as it's coming towards you, slewing sideways is getting harder to meet the target, but it's not nearly the same effect. So when you consider pointing as a resource, you're basically repeatedly solving these equations. And in fact, in our planner, we just repeatedly solve these equations on board using a standard Newton's route finding method. If we were to actually fly this, almost certainly we would take this and throw it into a few thousand entry lookup table, because you don't want to keep solving these equations. You would just develop your own approximation to the solution for those equations, right? This is a classic inverse problem, right? You're guessing at a solution and successively approximating it. Instead, you could just approximate it all with a huge lookup table. Well, okay, a few thousand elements. And so then, what do? We actually repeatedly solve this problem for a large number of targets and greedily try and insert all of these observations into the schedule according to some priority metric, okay? This is actually an animation of our flight software simulation. That's from an output of our flight software simulation. So this is showing an overflight. This is actually sped up at well over 10 times. And so this is showing all of the targets that were first scanning in this forward-looking part. And then as you see some of these later ones turn into green, those are the ones that are selected for revisiting, okay? And so the spacecraft is slewing forward, searching all these targets, analyzing them on board, and the particular software that we're using to analyze them is this mixture tune match filter. Then we slew back to hit those targets that meet the different criteria, that have the target signature that we're interested in, that have the interesting phenomenon. Note that in this particular demo, we didn't do this, but you can actually have the targets not literally be the same targets that you saw in your initial scan. So it could be a moving target. You could be estimating its motion and then have to hit and slew that moving target to image it later on. And this is actually very interesting from a lot of the different science phenomena that we're interested in. Plumes, volcanic plumes, different algal blooms. These are all things that are moving at the speeds that are enough to make a difference. So not only are we interested in this Earth observing context, we're interested in this for deep space context. So let's imagine we have a flyby here, like Hartley. We want to actually detect a target here, let's say a plume, or these bright spots on the surface of the object are also of interest. These are often surface volatiles, right? And the scientists want to image these with point spectrometers. So these are very narrow field of view instruments that are really only giving you 1 pixel of data. You can't map the entire body with that. So in a smart flyby, what we want to do is we want to fly by the object, do this broad multispectral scan, and then for the specific point targets that we see, we want to point to them as we fly by, okay? That's challenging for a few reasons. First of all, your flyby speeds are going to be pretty fast. Second of all, your spacecraft is translating, this target body is translating, this target body is rotating, sometimes quite fast. In the case of Churyumov-Gerasimenko, it's about a 12-hour rotational period. If your flyby is on the order of a few days, that's relatively fast. Also, you typically have illumination constraints. You want the sun to be in a particular orientation with respect to your surface target in order to image it and get the best data. If you really want to get complicated, this sun constraint is specified with respect to the surface normal of the target, not just its position. Okay? So if you really wanted to do the observation the way the ground scientists do it, you have to use a 3D model of the body, not this stick figure ellipsoid that I mentioned here, and understand that orientation constraint as well. That's, I think, well beyond the ability to do sort of on the fly automatically. So we actually have a prototype that's trying to demonstrate this. We have here the timeline-based planner, Aspen-Casper. We have GeoSketch, which uses different libraries from a geometric observation planner we have that's called Eagle Eye, developed by Russ Knight and others. We leverage heavily the C-SPICE reasoning set of utilities. Those of you familiar, this is a navigation and geometric reasoning package that allows you to understand, reason about all these different coordinate frames of reference. And then the visualization that you're going to see is driven through a system called Cosmographia. So what we do here is we plan the observations. Then as we get the data from those observations, we actually have an observation simulator. We get these targets. The targets have to then be translated from the image space, the line sample space, into the target frame of reference. In other words, this ellipsoid, we're assuming they're on the surface of the body. We then have to project forward using the spacecraft trajectory and the body trajectory and rotation, the times when the geometry is suitable for reobservation. Those are then converted to time intervals, as shown here. And then the Aspen-Casper planner schedules according to those time intervals. Okay? So basically, we take a baseline schedule, we take an initial trajectory, we have these different observations, we have DSN downlinks, we have other things, and the geometric constraints are scheduled according to the constraints associated with the different observations. We have this planner that dispatches the activities and then takes the new requests that come back from the observations. And so if we put that all together here, this is actually showing that exact scenario using Rosetta data. This is in Cosmographia. The blue lines are showing when we image with the wide field of view instrument. Then the yellow lines are showing when we actually see the target, when we see the event happening, which in this case is a synthetic plume. We image the base of that plume with a very narrow field of view instrument. And so we're actually using the instrument kernels, the instrument models of two actual Rosetta instruments. The wide field of view instrument is the OSIRIS camera. It's the visible camera on the Rosetta mission. And the narrow field of view instrument is the Moreau infrared radiometer. It's a long wavelength radiometer that's actually a JPL instrument. And it has a very narrow field of view, about 1/2 of a degree. And so it's kind of, I was probably talking too much during that, but you'll note that the spacecraft is flying by, it's going so close that it actually can't even keep the nucleus in the field of view. That's actually common for these kinds of high rate flyby missions. It's actually not accurate for Rosetta, but for something like the deep impact mission or something like that, your flyby rate is so high that you can't actually slew fast enough to keep the target in the field of view. So you have to pre-point it and then kind of wait for the target to slide through the field of view. So that's how challenging some of these geometric windows are. So both of these prototypes that I talked about, we brought them all the way into VXSim. And the reason why we did that is we want to actually benchmark them against existing flight processors. And both of these actually fit within the ballpark of cramming all of the autonomy software onto something like a RAD 750. Now, ideally, you would actually have a multi-processor environment. So on EO1, we're very lucky. There are 2 flight processors, 2 Mongoose M5s, which is a variant of a RAD 3000. One which runs all the traditional command and data handling software, and then there's a second one that we put all the autonomy software on. That's actually a very good idea from the idea of separating the autonomy flight software from the rest of flight software for many reasons, including that it's not competing for the CPU resources and so on. There's a lot of related work. I've mentioned earlier the autonomous science craft has been flying on EO1 for over a decade. That's a completely different regime for two reasons. We have the same software architecture, but it is not what we call geometry aware. It only knows of particular timings when it can view particular targets. So in other words, all of the geometry has already been compiled out into these particular timing goals that says you can image this target, but only at this exact second. That's for two reasons. First of all, EO1, we don't pitch forward or pitch back when we observe targets. It's only when it's directly, we only roll left and right to image targets, and then we use the push broom imager. We actually can't pitch forward. Well, we theoretically could. We do not operationally. The second thing is the response time is actually tens of minutes on board EO1, not anything like what we've been talking about. And that's not an Agile spacecraft, so that's actually fine. This is actually, the Lemaitre et al. Is actually a very good paper that really does a very good job formalizing the pointing as a resource observation planning problem. And then this is actually a generalization of that work that talks about ground planning for a constellation of spacecraft. There's actually an even better paper by Chien actually at Terra Bella, which is a Google company where they have a series of small spacecraft, a constellation of them, 7 right now, but they're hoping to go to like 30 or 40 of these, and scheduling the constellation's coverage of different targets, which is a very interesting problem as well. So this is hopefully going to be eventually part of a long line of autonomous systems that JPL has been deploying. But now, just in a little bit of the remaining time, I'm going to go completely wild here and talk about things that hopefully will inspire people to think really of autonomous systems in the large. And so the first is ocean worlds. So as we now know, there are a large number of worlds in our solar system that have liquid oceans. It's mind-boggling. We can go anywhere from Earth, of course, Europa, Enceladus, Titan. Now Pluto is considered a very likely candidate to have an ocean underneath it based on the fractal structure from the New Horizons data. Why are we interested in these ocean worlds? These are, according to now a larger and larger contingent of scientists, the most likely places where we might find life not on Earth in this solar system. I would refer you to, there's this great paper by Martin et al., which is a DNA-based analysis in Nature Microbiology. There's what's called last universal common ancestor. And so it used to be, the theory was, back before the 70s, life couldn't exist without photosynthesis, but that's wrong. Why is that wrong? Because they discovered life at these hydrothermal vents, it's spreading hydrothermal vents at the bottom of oceans in the 70s. No light, plenty of life there. Okay. What this Luca argument makes is now a leading theory in science is not only can life exist without photosynthesis, that's where life started on Earth. Okay? All of these ocean worlds, well, not all of them, quite a few of them are believed to be tapping into internal heat sources, like Europa is an example of one, Enceladus is another. That means it's very likely they would have hydrothermal vents and a liquid ocean. Therefore, they might have life. Okay? So that doesn't sound so bad. We want to go to one of these planets. Well, it's really hard. I apologize for this very old video, but this shows actually some of the difficulties of conducting such a mission. You have to fly to Europa. You have to land, which is really hard. The radiation environment is really bad. You now need to get through this ice cap. Well, there's a lot of problems. It costs tens of millions of dollars to melt through an ice cap on Earth that's maybe 1 kilometer thick. This ice cap is believed to be anywhere between 10 kilometers thick on Europa to hundreds of kilometers thick on these other planets. Once you get there, you basically have an ocean that, by the way, you don't know its composition. you don't know its current, you don't know its viscosity, and you need to basically fly around in this ocean and search for a hydrothermal vent. You will likely be able to communicate with the submersible on the order of once every few days to once every 30 days. Why do I say that? I say that because, first of all, it has to explore away from the point of entry. So you're going to melt through in this, if the teams that are working on the different melting strategy do their incredibly hard job, you'll get to melt through in one location, okay? In order to search for hydrothermal vents, you want to actually do what's called a latitudinally long survey. That means you want to go thousands of kilometers north and south from this location searching for hydrothermal vents. You now need to go away. Your mobility is not going to be, going at 700 miles an hour in this ocean of unknown substance. You're probably going to be going 1 or 2 knots or maybe even a fraction of a knot. So your voyages are going to be these small excursions longer and longer away. One of the challenges is, how do you navigate with only a single navigation point beacon, right? There are many challenges in how to do that. So, by the way, all of your data also has to be exfiltrated through the ice to an orbiter that then gets relayed back to Earth. So when you do all of those configurations back, you get that this vehicle is going to have to be autonomous for days, perhaps months. Now, we actually have a very good starting point. There are right now autonomous marine vehicles that do this on a routine basis on Earth. However, they cheat in several fashions. Number one, they use GPS for navigation when they surface. We don't have GPS, obviously. And the single point navigation is actually particularly challenging. Also, they use iridium to exfiltrate their data. Obviously, there's no iridium at Europa, Triton, or whatever. So we need to get this data back. So these are some of the challenges that would face us in flying such a mission. But just so you think this isn't pure science fiction, one of the people on my team just returned from an exploratory. It's funded by a program called A-STEP, which is an astrobiology program. They had the Polar Stern, which is a German icebreaker, investigating the Jurassic Massif. This is the world's only known sub-ice hydrothermal vent. It's a few hundred kilometers from the North Pole. This is the vehicle they use. This is a vehicle built by the Woods Hole Oceanographic Institute. Antje Bodius of the Alfred Wegener Institute was the PI for the cruise. Chris German is actually the lead for the hydrothermal vent hunting expedition. Kevin Hand of JPL, a very well-known astrobiologist, was one of the key scientists. This is the map that they brought back. These are some of the samples that they brought back. It's quite likely they discovered a few new forms of life there. That's what happens when you go to these hydrothermal vents that have never been explored before. And literally, the person on my team who was there was studying what the scientists, how the scientists and engineers searched for the hydrothermal vent and how they did the scientific exploration. And to give you the 2-sentence summary, it's a bunch of nested lawnmowers. So the lawnmowers are grid searches where they search large areas, and they do a bunch of nested lawnmowers. They do a large-scale one with a larger gap at a higher altitude, further off the deck, further away, because that's safer, and the vehicle can operate more autonomously. And then they look for anomalies like thermal anomalies, chemical anomalies, and then they use those to hone in on a smaller area where they do a more focused nested search. Okay, what are the problems with replicating something like that on Europa? It's really hard to do a lawnmower without precise navigation, right? We are not going to have anywhere near the sensing suite that Nereid Under Ice has. This is a vehicle that's often teleoperated. It's actually only autonomous in the most dire of circumstances. And so we have our work cut out for us. And if you thought that was too much, what's the ultimate challenge for an autonomous mission? An interstellar mission. So I'm very lucky to have been fortunate enough to actually talk to some people on different concept studies and things like this. This slide is now out of date because we actually know several planets at this solar system. But in the most optimistic cases, you have a cruise period of decades, 40 years, 60 years, 80 years, 100 years, okay? So your spacecraft is pretty much on its own for decades. So it has to be very reliable, autonomous, deal with whatever happens. Okay, so maybe you're an optimist and you say interstellar space is boring. That's just a hardware problem. Once you get into the new solar system, what do? You're going to have much more precise information about the orbits of these planets. What planet do you try and orbit? You have to autonomously figure out how to get into that orbit. What do you want to look for? You want to look for signs of life, intelligent civilization. What does that look for? These are unbelievably, ridiculously open questions, right? That it'd be fun, maybe, you know, if there's an open bar tonight at the dinner, we can all talk about this and figure out. So these are the kinds of questions that I think in the long term, when we think about autonomous systems and flight software, where we want to go. So I just wanted to summarize by saying, in the near term, one of the things to me that is very exciting is to try and take these autonomous systems and make them much smarter in the operational context of people operating these spacecraft. And for us, that's meant making them smarter geometrically. Spatial awareness of the system is really hard. It integrates with navigation, it integrates with pointing and slewing. This is one of the big things in autonomous systems for spacecraft. For low Earth orbit, the time responses are actually quite challenging. You're talking about being able to do responses in tens of seconds for the software so that everything else can do its job. Your image processing can do its job, your AACS and so on. For future missions to ocean worlds or interstellar missions, these are unbelievably challenging from an autonomy standpoint, and we need to be thinking about them now so that we could, in fact, do something like this. And I've talked a little bit about some prototype flight software and talked a little bit about what some of the state of the art is and some of the things we're doing. And so with that, thank you very much for your attention, and I appreciate you all getting up for an 8 o'clock talk here, and I'd turn it over to questions. And if we have any, budding billionaires in the audience who want to fund that mission, let us know, of course.
Questions? Here. Oh. Here you are.
Okay, thanks. It's a good talk. This is more an observation, I guess, than a question, but I'm aware of the fact that the high-performance computing community is very interested right now in increasing the performance of low-power devices, motivated by the fact that we all have cell phones. So it seems like at some future time it may be possible to put quite a lot of processing power on a spacecraft even with low energy available, and that might have an influence on some of the stuff that we talked about here today.
So I mean, absolutely, but this is what gets me into arguments with high-performance computing people all the time. I think right now, existing in what you see on spacecraft, there's right now as we speak a gap between the kinds of capabilities that are technically feasible and the kind that we see on everyday missions. So right now we're limited by conservatism, lack of awareness of what the technology can do, different things like that, more than we are by the existing CPUs. Now, that's not to say that, let's say, we have this burgeoning revolution over the next 5 years, that we wouldn't be processor limited. I would say mostly the people who could best use that, the increase in processing power is on the instrument processing side. So in particular, certain instruments, hyperspectral, radar, synthetic aperture radar, LiDAR, there are some things that you want to do to process those on board that would be very computationally intensive. But for example, on UAV SAR, they even have real-time SAR processors, and I don't even know if they literally have a real-time interferometric product yet, but I know they're very close if they're not there yet. Now, they've gone the approach of using custom hardware in specific FPGAs, but I would say that more computing power would be very helpful, but I wouldn't say that that's the tall pole. I would say the tall pole is the willingness to embrace that this is a very different way of running a mission, conceiving a mission, of flying a mission, and jumping in both feet with that.
The people who are trying to melt through the ice, have they read Tom Swift and his Atomic Earth Blaster?
I don't know. I know there are multiple approaches to melting through the ice. I believe there are 3 just at JPL, but I think there's a large number of approaches to melting through the ice that involve things like particular kinds of lasers and mechanical actuation, a purely thermal approach. There's no shortage of ideas, but it's incredibly challenging. And you know, the good side is that we have a lot of ice, at least for now. We have a lot of ice on the Earth to practice on. And there's a lot of people who are looking at this. So we have a proposed experiment where we would send sea gliders underneath the Antarctic ice shelf, and just to burn through, you know, let's say 60 to 100 meters of ice is millions of dollars right now, and that's on Earth, right? With effectively infinite power. The other big question is RTGs or not. Are the RTGs allowed in Europa? And I've heard everything all over the place. To me, common sense dictates not, because you don't want to leave an RTG on a habitable world, right? In an environment where it's not going to just sit there forever. This is not like leaving an RTG on Mars, where we know the environment, it just sits there. You're leaving it in a liquid that's God knows what, right? Yeah. But I'm very happy that that's somebody else's problem of melting through the ice.
Other questions?
Other questions?
Yes.
Thanks for the talk. I appreciate it.
Oh.
In sticking with the software theme, I was wondering if you could speak to a little as far as the complexity of the calculations, the geometry, the image processing that you've talked about, and the autonomy there. How did you move from a desktop sort of situation, probably written in MATLAB or something like that, and getting it into a C flight software environment?
Okay, I'll start by making a little nit here. Almost all the software that I talked about here is in C++, not in C. Now, to me, that's not a big difference, but then to other people, that would be a religious war. So it's just a lot of engineering work, like you're talking about. So you take something that's in MATLAB, or in many cases in Envy, you know, Envy/IDL, and the first step is you have to analyze it from an algorithmic standpoint. Does that completely blow you out of the water? And that rules out a lot of things immediately. I don't think we've found that the computing limitations are the hardest limitations. To us, I would say the hardest limitations are the fact that the flight software environments that you're typically looking at with an RTOS and embedded processor, your board support packages and everything, are fairly hostile. Let's compare that with Linux or Mac OS on your laptop. And so I'm a big fan of taking all of the science processing and even some of the higher level autonomy like the planner and running it on some kind of commercial OS like Linux, or at least something more Linux-like. And at the risk of getting in trouble here, RTEMs, not other things. Because I think it's underestimated just how much work that is for some of the embedded software development teams. And then it also opens up a larger community of people, right, who can work on it, who are more used to that tool chain, that environment, and so on. Does that answer your question?
Yeah, pretty much. I was wondering if you had any tricks as far as moving from one to the other.
Well, I think my answer said the trick is to decrease the distance between one and the other as much as possible.
Lots of engineering work.
Yeah. Yeah, but we don't have any magic bullets on that. I wish we did.
Any other questions?
Here you go. I was going to, I'm the RTEMS project lead, so you looked over at me, and I'm going to thank Isa. Isa has done a lot of work on symmetric multiprocessing tools for RTEMS, and a lot of the things just, the current like GCC just builds out of the head with OpenMP, completely supported and tested, scaling linearly up to 24 cores. A lot of stuff they've been looking forward. We may not know exactly what we wanted, what we'll actually fly and believe in, but all the tools that have been used in parallel and distributed computing that makes sense to bring down, and all the research that they've done to make sure their systems are correct, that's really what we have now. When you end up with 24 cores or 32 or whatever you've got, that's basically 10 years ago what the supercomputing world was using.
Yeah.
And those tools are mature. So it's not that different. It just it's far, the whole parallel distributed computing is foreign to us as embedded people. It's all
Yeah,
a new
although,
world.
although to be very specific, I'll return to the answer I gave earlier. I think going multi-core, obviously you'd rather have more cores rather than less, but it takes some work to actually correctly use the power of multi-core. And mainly what I was beating on was saying, why can't we just fly in vanilla Linux? And speaking as somebody who's been the PI of a CubeSat where we literally did fly vanilla Linux, I would still push for that. Now I'm sure there are all kinds of control people who will tell me, no, I'm insane, I don't know of this, that, and the other thing. But then there should at least be a discussion about what percentage of the flight software needs to be in an RTOS, and then if you can separate those, then you can have a more civilized discussion on maybe 80% or some large percentage of the flight software can be on a vanilla OS. I think that's at least a discussion. Sorry.
Yeah, just a quick thing. So we've been investigating partition systems. So
Yes.
hard real time sitting on this partition, then
Yeah.
vanilla Linux sitting over here for the science guys. And AES at JSC is funding some of that activity. So we expect to have something at the end of this year to demonstrate that you can crash
Yeah,
in that partition Linux, and then we'll bring you back up.
exactly.
So that's the way to go to make the distance between what they do when they're on their desktop and the flight domain
Yeah.
a lot less.
Exactly, and I would draw parallels to, now virtualization is everywhere in the commercial world, right, in the server world. And so if we can bring that to the flight processors, then effectively that's going to be a big win for everybody, right? Other questions?
Okay, other questions? Nope.
Okay, I would encourage people, if you have other questions, just accost me later in the day or tonight. I actually have to run back to JPL for a meeting, but then I will be back here, so
Okay, thank you very much.
thank you.